The eye at Paraim has returned, but its string is glowing brighter, pulsing with strange energy after it tripped behind the sun. When China's Deep Space Array intercepted a transmission from 3I-ATLAS, the data looked impossible. A triad of light-frequency pulses repeating in Fibonacci intervals. That meant prediction or control. Within hours, the feed was sealed and every foreign relay went dark for an object believed long extinct beyond Mars. 3I-ATLAS was suddenly active again. If it wasn't reflection, who or what was sending back across the void? Uncatalogued entry. In late June 2025, survey telescopes in southern China recorded a faint object drifting against the backdrop of the star. At first, it looked ordinary. Another small body sliding through the field of view. But the numbers wouldn't cooperate. When analysts plotted its course, the path refused to form a closed loop. Objects bound to the sun always curve back. This one didn't. It was moving too fast and from the wrong direction entirely. Each recalculation pushed the inbound velocity higher until it stabilized near 68 km per second, faster than anything native to the solar system. That single figure changed its category. It wasn't a comet from our outer regions. It was an interstellar visitor approaching on a one-time trajectory that would slice through the inner planets and leave forever. When the Atlas network in Chile independently confirmed the track on July 1, Chinese analysts already had several nights of data stored under a provisional tag, non-periodic hyperbolic transient. The label was intentionally plain. Behind it sat coordinates, magnitude curves, and an early spectral scan showing an odd signature strong in carbon dioxide nearly absent in water vapor. Comets normally show the opposite ratio. That chemical imbalance made the object scientifically interesting, but one feature made it difficult to classify. Its light changed in a rhythm that didn't fit natural rotation. A normal spinning body brightens and dims irregularly as sunlight hits uneven surfaces. 3I-ATLAS produced short even oscillations, not random flickers, but measured beats that repeated with uncanny stability. To verify it, the Purple Mountain Observatory in Nanjing arranged extended night runs while auxiliary stations in Yunnan and Xinjiang filled the gaps. Optical coverage soon merged with radio observation blocks from the FAST telescope in Guizhou, which listed its sessions as calibration tests, but targeted the same coordinates. Those runs created the first combined optical radio dataset on the object. No public report mentioned the overlap. The international brief released weeks later reduced the discovery to a line of text. Non-gravitational acceleration consistent with volatile activity. What it didn't mention was the steady pattern still appearing in China's recording. A signal faint enough to ignore, yet too consistent to dismiss. By the time most telescopes turned away, Chinese instruments were still following it frame by frame as it crossed into the inner system, the pattern in the data. Tracking a distant object isn't about seeing light. It's about measuring how that light behaves. Every second, telescopes record changes in brightness and timing, and those variations reveal what the object is doing. A tumbling rock produces irregular flashes. A venting comet shows random spikes caused by gas jets reflecting sunlight, but the light from 3I-ATLAS didn't behave like either. During consecutive nights of observation, instruments at the Purple Mountain Observatory in Nanjing began registering a rhythm. The brightness rose and fell in perfectly even intervals. At first, the intervals seemed harmlessly short, a few seconds apart, but they repeated too precisely to ignore. Analysts isolated 3 consistent gaps between peaks, 5 seconds, 8 seconds, and 13 seconds. Each new pulse followed the sum of the 2 before it, a pattern that mathematicians call the Fibonacci sequence. The Fibonacci sequence is one of nature's quiet signatures. The spiral of a sunflower, the shape of a hurricane, even the arms of a galaxy, all grow according to that same expanding ratio. It's the mathematics of balance, not random, but ordered. Finding it in biological growth or physics is normal. Finding it in a stream of reflected light from a comet-sized object moving through interstellar space was something else entirely. The data were rechecked against all known sources of interference. Instrument error, none found. The pattern appeared across multiple independent sensors. Atmospheric turbulence, impossible, because the same timing was detected from observatories separated by more than 1,000 km. When engineers compared the light readings to recordings from the Fast Radio Telescope in Guizhou, they found a faint but measurable radio fluctuation that matched the same 5813 rhythm that ruled out coincidence. The modulation was real. No one knew what caused it. Cometary jets can create irregular flickers, but not with this precision. Rotational tumbling can mimic periodic light curves, but the intervals would stretch or shrink as the body spins, not stay locked in sequence. The readings were clean, mathematical, and consistent across instruments operating at completely different wavelengths. The results were stored, but never published. The official Chinese bulletin issued in late August mentioned only non-gravitational acceleration consistent with volatile activity. The same phrasing used for any active comet. The underlying rhythm, a pulse that matched one of the oldest mathematical sequences known, remained absent from every public archive. Whether that omission was cautious verification or deliberate silence is still unknown. But by the time 3I-ATLAS slipped behind the Sun, the pattern had become clearer, not weaker. The rhythm held steady until the last recorded signal, as if whatever was generating it had a reason to keep time. The Fatima timing, the light curve sequence that revealed the Fibonacci rhythm, reached its cleanest form on October 13, 2025. For the technicians analyzing the data, it was just another date on a long observation list. Only later did someone notice that the timestamp carried a strange historical echo. October 13, 1917, the day of the reported miracle of the sun at Fatima, Portugal, where thousands claimed to see the sky flash. The coincidence drew attention because 3I-ATLAS was positioned almost directly behind the sun on that very anniversary. From Earth's viewpoint, its outbound trajectory lined up along nearly the same solar longitude recorded in early 20th century charts. The geometry was simple but exact. One object disappearing behind the sun while another a century earlier was said to have pulsed before it. No one claimed connection, but the timing was unusual enough to note in the log margins. What mattered scientifically was the pattern itself. The pulses from 3I-ATLAS repeated with clock-like precision. 5 seconds, 8 seconds, 13 seconds, then a pause near 34. Each number following the Fibonacci sequence. A mathematical series where every term equals the sum of the two before it. This sequence isn't obscure trivia. It appears in the growth spirals of plants, the curvature of storms, and even the spacing of galactic arms. It's nature's way of distributing energy evenly through space. Detecting it in reflected light, however, required an emitter capable of keeping time to fractions of a second. Engineers tested every conventional explanation. Could a rotating body produce that rhythm? Not likely. Rotation would gradually stretch or compress the interval. Could outgassing jets modulate the light? Only if they fired in perfect order, which no comet has ever shown. Instrumental error was ruled out when both optical and radio arrays captured identical timing from separate locations. By the end of that 48-hour window, the pattern was stable enough to form a complete waveform. Then the object passed fully behind the sun and all direct observation stopped. The last frame showed the pulse sequence tapering but not ending, as if the signal had simply slipped out of range rather than ceased. To anyone studying the data, the meaning was still unknown. But the timing down to the minute was now part of the record. On the same date once associated with unexplained solar flashes, an interstellar object emitted light in the exact numerical rhythm that shapes patterns across the universe. The CO2 anomaly chemical composition is the most revealing fingerprint an object from space can carry. When sunlight hits a comet, molecules in its surface ices vaporize and scatter light at specific wavelengths, forming a spectrum that acts like a barcode of what it's made of. Most comets release large amounts of water vapor mixed with traces of carbon dioxide and carbon monoxide. 3I-ATLAS did the opposite. It produced strong CO2 emissions and almost no measurable water, a ratio nearly 20 times higher than the norm. The first confirmation came from infrared data gathered through mid-July, which showed a band near 4.26 micron, the signature of carbon dioxide gas. Normally that signal weakens as a comet nears the sun and its water content dominates. Instead, 3I-ATLAS maintained a constant CO2 peak even as its total brightness change, suggesting that the gas wasn't coming from frozen surface ice, but from deeper layers or trapped reservoirs that vented in precise interval. When Chinese observatories compared their optical readings with international infrared data, the results diverged. The Western datasets showed an ordinary decline in brightness consistent with distance. China's logs showed short surges, tiny increases in intensity that lined up with the object's earlier rhythmic pulses. Each CO2 emission spike matched a moment when the light curve briefly sharpened, implying that whatever was controlling the rhythm might also be influencing the gas release. To test that link, the Purple Mountain Observatory coordinated simultaneous spectral runs at different exposure times. The aim was to separate natural venting from pattern emission. The resulting graphs displayed a repeating phase shift, a half-second offset between visible and infrared peaks. No known physical process on a tumbling comet could produce that alignment with such accuracy. Internally, the readings were labeled non-thermal modulation of volatile release. A cautious phrase meaning the gas variations weren't tied to sunlight or temperature. The data packet containing those results never appeared in any public archive. Instead, later summaries condensed the finding to a single sentence. Composition dominated by CO2 with minimal H2O activity consistent with typical outgassing behavior. The simplification hid what the raw spectra implied, that 3I-ATLAS wasn't simply venting gas. It was controlling it. By early October, as the object receded, the CO2 line weakened, but the modulation persisted. Each drop in brightness followed a measurable repeating delay, as though the source of the emissions operated on a schedule rather than a chemical reaction. To the instruments, it looked mechanical. To the logs, it remained chemical. And in the gap between those two interpretations, the story of 3I-ATLAS grew stranger. The suppressed memo. The first internal summary describing 3I-ATLAS's irregular emissions appeared as a 4-page technical note circulated inside the Chinese astronomical network. It was routine in format, timestamps, spectral ratios, correlation charts, except for one short line buried halfway through the third page. Translated, it read, "Missions exhibit structured periodicity inconsistent with sublimation dynamics." In plain language, it meant the object's gas output didn't behave like melting ice. It followed a pattern. Within hours of distribution, that memo was replaced by a revised version. The same figures remain, but the sentence on structured periodicity was gone. The file name and release date stayed identical, as if the earlier draft had never existed. Only a handful of recipients still had the first copy saved locally. One of them archived it in a secondary research log, which is how it survived long enough to be referenced later in footnotes. The redaction didn't go unnoticed. Analysts comparing internal datasets found that several observation records from late August carried identical check-some-value digital fingerprints that confirmed the files had been rewritten rather than appended. That suggested active editing rather than routine revision. The version still available to the public stripped out all mention of emission intervals and retained only averaged intensity values. Please like and subscribe.